All right, this is Physics Unit 3, video number 4. We are beginning to talk about Newton's laws of motion. So a quick intro to Newton's laws of motion. These were made by Sir Isaac Newton, and he lived 1642 to 1727. He literally wrote most of today's physics book. Everything motion related comes from Sir Isaac Newton. In an 18-month leave of absence from college teaching, leave of absence in quotes, the plague was going around Europe and everybody stayed home for 18 months. So he wrote the book on physics during a pandemic. What have we done during our pandemic? Well, we didn't write a physics book. During this leave of absence, he did a bunch of things. He uncovered the secrets of gravity. He discovered the nature of light and optics. And he invented calculus. Not bad, huh? He investigated why objects move as they do and published a book in 1687 called the Principia, which outlined his laws of motion. These laws still guide the universe and are important to rocket scientists, quotation mark, today. You will be required to state all three of Newton's laws and apply them to motion problems. Newton's first law of motion. Newton's first law of motion is called the law of inertia. Inertia is defined as the tendency of an object to remain as it is, either at rest or in uniform motion. What does uniform motion mean? Constant speed, straight line. You experience inertia riding in your car. To remain at rest. So let's say speeding up. Speeding up, in order for your body to remain at rest, you lean back. It feels like you're being pushed against your seat, but your body is trying to remain at rest. So you're leaning back. To remain in motion, when you're stopping, you lean forward. Or if you're turning, your body wants to go in a straight line, which is why you lean right when turning left. The amount of inertia of an object varies. Which has more inertia, or that is, which is harder to get moving if it's at rest, or to get stopped if it's moving? An empty truck or a loaded truck? Which one is easier to get moving? Which one is easier to stop? Which one is harder? It's the loaded truck. The loaded truck is harder to get moving. It is harder to get it stopped. If you're a football player, you hit somebody. Is it hard? Which one is it harder to get moving? Somebody at rest. Is it harder to move a 100-pound person at rest or a 200-pound person at rest? It's the 200-pound person. I'm going to change tabs real quick. This is Newton's first law of motion according to Garfield. It says, I happen to be conducting a scientific experiment testing the first law of physics. Bodies at rest tend to stay at rest. So Garfield's statement of the first law. Bodies at rest tend to stay at rest. Garfield left some things out here. For instance, bodies in motion tend to stay in motion. Our statement of Newton's first law. An object will remain as it is, either at rest or in uniform motion in a straight line, unless acted upon by a net force. A net force means an unbalanced force. So, real quick, let's flip back to page 2. And you should have this filled in, adding forces, part A and part B. We said that this one was a 110-pound beast. This is the force. It was the sum or the resultant, which we also probably wrote down. And this is the net force. So we can add that in. It's the net force. Part B was 10 pounds west. This was the net force, because these were unbalanced. This law says that being at rest and being in uniform motion are the same as far as forces are concerned. If you remember the example of the two people on the train car, where the observer was standing alongside the tracks, whether you are at rest or in uniform motion depends upon the observer's frame of reference. The two people on the train were throwing the ball back and forth, and the ball was behaving the same as if they were at rest. Being at rest and being in uniform motion feels the same. If you are at rest, there is no net force acting upon you. If you are in uniform motion, there is no net force acting upon you. True or false? If an object is at rest, there are no forces acting upon it. The answer here is false. So we can draw some what we call force diagrams. So here Here's an example. This is a book on a shelf. So here's the book. Here's the shelf. There is no net force, but gravity is acting on the book. And something is keeping gravity from pulling the book down. There are forces acting upon it, but since it is at rest, there is no net force. Here's a force diagram. This is one that we'll have as a demonstration in class. Here's a student. They are holding on to one rope here, one here, and we're not going to pull so hard to hurt their arms. But we're going to exert a force. So here's the force in one direction. Here's the force in the other direction. If these two forces are equal, and based on the drawing of their vectors, I would say they probably are, there's no net force here. The net force equals 0. There are other forces at play in this example too. For instance, if this were the person's body, the person has weight. Just drawing it like this would imply an unbalanced force. The person is not falling. Something has to be keeping them from falling to provide an equal force so that the net force is 0. And that is the floor holding them up. So these two forces have balanced each other. The weight and this force have balanced each other, and the net force is 0.